All right. Let's do some sound check first. Hello. Okay, Pete, can you hear me?
Yeah, yeah, I can.
Okay, okay, great. All right, everyone. Before we start with the guest lecture, I would like to introduce our speaker today, Professor Pete Burnap from Cardiff University. So Pete Burnap is Professor of Data Science and Cybersecurity at Cardiff University. He is the Director of Cardiff's NCSC EPSRC Academic Center of Excellence in Cybersecurity Research. And he also leads AI for cybersecurity research at Airbus DTO on a part-time secondment basis. And he has been involved in grants in worth in excess of £23 million, leading large awards from EPSRC, ESRC, and industry on cybersecurity analytics, the fusion of AI, cybersecurity, and risk. And he sits on the UK government AI Council. And today he will be talking about AI for cybersecurity innovation. So without further ado, Pete, the time is yours.
Thanks, Adi, and thanks for the invitation, and hello everyone, and thanks for joining. So yeah, as Adi said, I'm Pete Burnap. I'm Professor of Data Science and Cybersecurity at Cardiff University, where I lead the Centre for Cybersecurity Research. Just for a bit of context, I suppose, the National Cybersecurity Centre is the UK's sort of leading authority on cybersecurity matters, and they have a number of what they call academic centres of excellence in cybersecurity research, which are sort of recognised based on a track record in cybersecurity research, a critical mass of people working in that area and publishing in that area, a significant flow of PhD students through the centre, and sustained through external grant income. So it sort of shows that our recognition at a national level on that basis. So yeah, I'm going to give a bit of an overview today on what we do basically at Cardiff, with a view to sort of opening it up as an open door for collaboration. You know, we're always happy to work with people and really keen to get different perspectives on what we do. So I'll give you a bit of background on what we do, and then I'm going to sort of give you some examples of the work that we've done around AI for cybersecurity innovation, both in terms of attack detection, automated response, and a little bit then around the security of AI itself. So I'm not going to go into too much in terms of technical detail today, because you can obviously read those in your papers. I'll just give you an understanding of what we do. So just to give you a perspective, I suppose, in terms of where we fit into the UK landscape. So the UK government has a national cybersecurity strategy. You'll note it says 2021, that's this year, and is about to be refreshed. But as part of that 2021 vision, there was a focus on essentially standing up the National Cybersecurity Centre, which is a public-facing arm, I suppose, of the government. Really there to sort of advise and disseminate guidance to everyone, from the individual small companies up to large companies, and part of their remit is what they call active cyber defence, which is essentially threat hunting, identifying threats, bringing them down, you know, communicating what the risk of these threats actually is. So alongside that, the UK also has an industrial strategy, which is around commercializing the world leading cyberspace and building on areas where the UK believe we have competitive advantage. And one of those areas is artificial intelligence and the data economy. And so that was published in 2017. And I guess, where we fit into this from the university level is that a lot of the work that we do is supporting the National Cybersecurity Centre vision for active cyber defence and building on that AI industrial strategy to use AI or machine learning specifically, but actually now moving towards what you might call AI, which is the more representation and reasoning world, for threat intelligence. So understand the cybersecurity landscape, understand how that might impact us as a business, as individuals, and where we sit within that, and sort of how to respond to it and sort of manage this growing cyber threat and ever-changing cyber threat in an ever more connected world. So that's sort of where we fit within that. So we use this term cybersecurity analytics. And essentially what we mean by that is this combination of, I suppose, what you might traditionally think of as analytics in terms of machine learning, where we've got computational mathematical models, some, at the ML side, artificial intelligence, but it's also trying to drive that through a theoretical lens. So we do a lot of work with our criminology partners. So for example, if we are trying to identify features that we might use for machine learning, we can try and use criminological theory of trying to perhaps understand motivations for cybercrime and try and use features in the data that we collect that might be indicative of criminological motivations. Similarly, the other side, when trying to understand why something is a cyber attack is detected through machine learning, it helps to interpret the outputs through a criminological lens. Similarly, in psychology, trying to understand susceptibility to cyber threats. So what might an indicator of something that might be an indicator that is a psychological susceptibility? Individuals and groups behave differently. How do we sort of include features theoretically, both in terms of building models and interpreting models that might be indicative of that? And similarly, well, what do we do with this? So we've got a machine learning telling us that there's an outcome. We might want to even do an automated response. How do we sort of bring that into the human-driven world, which again brings in the psychology aspects of trust and collaborative working, as well as sort of international relations. So if we're doing sort of considering the political element, as well as the sort of different cultures around the world, how do we bring in AI cyber defense into that? So that's what we mean by cybersecurity analytics. It's that sort of fusion around, if we've got AI, how do we drive that through a theoretical lens, and how do we bring people into it? Because otherwise, frankly, it's not going to work. So this slide is basically our center in a nutshell and everything that we do. I won't go into it in great detail, because as you can imagine, as it says, there's 50 researchers working on this. It's very difficult to sort of cover everyone's work, but this gives a broad overview of what people do. So we start with risk assessment and modeling. So we try and understand where risk may impact us, again, as both individuals, small companies, large companies. Traditionally, risk assessment is done on a sort of an asset basis. You understand your assets, you understand the vulnerabilities to those assets, the threats that might exploit those vulnerabilities, and then there's various combinations and permutations of deriving impact from that. But one of the issues with that is, well, one, from a cybersecurity perspective, you can't always know what your risks are. Cyber threats change, when you have sort of almost inherent built-in vulnerabilities that you might not even know about, whether that be through legacy code or device issues. So we sort of try and think about that. And also there are interdependencies between assets as well, right? So, if you've got several assets or hundreds or thousands of assets running a business process, you really need to know what the interconnectivity is. And so if one asset fails, it's not just about the impact of that individual asset, it's about the impact on the wider ecosystem. So we've sort of done work around goal-oriented modeling and trying to understand what the overall goals of an organization or process or business are, and try and ask the question around, well, what needs to be working for that to be operating? And that is an iterative question. And you can start with the overarching goal of a system. You can ask the question, what's the high level needs for this to be operational? And then you can ask for each of those high level needs, what does that need? You can basically ask the question of what needs to be working and what does that depend on, which We've then enabled a sort of a toolkit to do that in a top-down manner and capture it in a sort of a graph, a directed graph, top-down. And that then lends itself well to conditional probability. So you can actually say, well, if something way, way further down in the graph fails or is likely to fail, you can change the probability of that. You can then see that direct cascading failure back up the tree into the goals. So you can see a direct impact on your goals of your wider ecosystem. So it's really trying to consider risk from an interdependency and from a very broad perspective. The middle arrow there is around communication and decision making and governance. How do people make decisions? Why do they make decisions? Who talks to who around cyber attack? And there's a lot of work going on in there around the criminology and psychology element. The third pillar then is the AI and data-driven analytics. So this is looking at collecting data from networks, from devices, from behaviors to basically build machine learning models to detect and respond to cyber attacks. So cutting downwards through all of that is this sort of idea of privacy and emerging tech. So all of this, right from risk, communication, decision-making, and AI detection and response, is different for different emerging tech. So IoT, cloud, automotive, we look at the full spectrum, and we're always horizon scanning as well for the next sort of emerging tech. And privacy also runs through all of it. So privacy with regards risks, privacy with regards decision-making and communication and governance, and privacy with regards data and machine learning models, both in terms of the data themselves, so where we collect them from and not identifying individuals, but also from machine learning and making sure that we don't have models that we can extract privacy-related information from. So cutting through all of this the other way, in the other direction, is the human factors bit. So understanding susceptibility of individuals, groups, individual differences, motivations behind behaving securely, but also motivations behind cyber attacks themselves, dynamics and social factors, and understanding the sort of toing and froing of this very complex socio-technical system that we've developed over a number of years and is continuing to be more interconnected and digital into the 2020s. So that is essentially the broad spectrum, and I just wanted to note as well that it's iterative. So you can see the arrow coming out of the last box around the artificial intelligence comes all the way back around to risk assessment. So our philosophy is not just to sort of raise awareness of attacks, but also tell you how that may impact you. What might be the risk be? How do you communicate that risk, and how do you make decisions on what to do based on an artificially intelligent alert? So we have a strong relationship also with Airbus, as well as other partners, including the likes of Thales, BAE Systems. We're very industry focused. We've sort of transitioned a lot of this stuff into Airbus. So the AI part and the risk assessment part are being used by Airbus. And we're also working with Airbus on understanding security policies and security culture, and looking at how we can create a more secure organization. Both of those areas have meant that Airbus have sort of created a strategic partnership with us. So we have our Airbus's only Centre of Excellence in Cybersecurity Analytics is at Cardiff University, and we also drive the Airbus Human-Centric Cybersecurity Accelerator. So we're both looking at the data and AI side, as well as the human factors and psychology side. There's a bunch of other things and stuff as well that we do, but essentially captures what we do in a nutshell. So now I've given you a sort of an overview. I'll go into a little bit around what we've actually done, and this particularly focuses on a case study around Advanced SOC Security Operations Center with Airbus. But this is quite a general approach. In theory, this could work for a number of different areas. And again, as I mentioned earlier, this could apply to IoT, enterprise networks, in theory, also operational technology and industrial control systems, which we're working on now, possibly even connected autonomous vehicles, right? It's the same principle. Which is that the problem is that you've got network intrusion systems, detection systems that these do fine-grained network analysis. They look at the data level, the protocol level, all of that kind of stuff. And you've got AV tools, which attempt to match code signatures to a list of known malicious code, right? So you have your known malware. You keep updating the signatures regularly, and you keep matching incoming files to your AV to try and block it and quarantine it if you think it's risky, similar with network intrusion data, right? But the problem is attackers are developing more sophisticated methods to avoid this detection. So you've got an EXE, you've got the code within it, but APTs and just malware more generally also obfuscating much of this. So you can do encryption, you can have custom code bases, you can do in-memory execution, you name it. it's becoming increasingly more difficult to just say, right, look at the code and map that onto AV, or look at the network traffic and sort of, associate this with malware. It's problematic, right? So we need to think about, if we're sort of having SOC, a security operations center, that often uses these off the shelf, AVs and network intrusion detection tools. How can we actually get that up to this sort of modern era, I suppose? How can we learn what is malicious and what is not malicious without depending on code mapping and fine level network analysis, where that information is obfuscated? I mean, okay, it's not obfuscated in all cases, but we know full well that over a very short period now, these tools are going to become very difficult to detect some of the advanced persistent threats that we're seeing. So it's good. Going back a number of years when we started this, now there was a paper published that looked at what was called the Big Four APTs, and they were basically making recommendations on what can we do to look at APTs, and they suggested essentially, if we want to do something on a system, we're going to leave a footprint. This is going to leave a trace. We have to, right? If you're going to, for example, exfiltrate some data from a system, you're going to have to escalate privileges. You're going to have to interact with the database. You're going to have to send that database out on the network. So, or at least the data from it. So we sort of came to this sort of idea of using system level activity metrics. So CPU use, either user system level, RAM use, your packets and bytes in, packets and bytes out, number of processes, quite a small amount of data, but using these low severity events that was recommended by that Big Four paper, that are inevitably generated when you run the executable. You can't actually create malicious activity without doing something on the system. So can we use what's left on the system when doing that malicious activity, and can we distinguish that malicious activity from what would be trusted or non-malicious activity? So it's analogous, or the analogy we used at least, was to try and theoretically ground this in the concept of DNA. So if you have two family members, if you take this DNA samples, they may not be exactly identical, but they'd be very, very, very similar. So it's a similar principle. So if you've got malicious behavior that you've detected through its low-level system events on a system, even if they change the code base, even if the code base is encrypted, even if you're doing in-memory stuff that you can't detect, the theory is that the behavior left on the system will match a DNA profile, even if it's done in a different sequence, because you'll be able to map it on top of the other. So that was the sort of principle behind this. And could we then essentially create this sort of form of DNA analysis using these characteristic features from the system? So how do we do that? This was basically the principle. So I'll explain this in detail in a second, but essentially what we've got here is two grids. The one grid represents what is good behavior, and the other grid represents what is bad behavior. And we basically mapped the processes, the user CPU, the memory use, the swap use, the packets and bytes onto these two maps. And in theory, what we're saying here is that these maps represent zones of activity: malicious activity, benign activity. The more bright the color is, the more frequently that activity has landed in that zone. So the bright green dots represent really frequently seen good activity, and the bright red dots represent really frequently seen bad activity. And these are driven by thousands of executables samples. So the question is, how do we cluster into these activities, which is what I'll explain now. So the diagram in the top left here is basically malware activity data for one piece of malware over 5 minutes. This is collected at a second by second level. So you can see over time what the difference is. And you can see that about halfway through, the CPU use jumps up as it does at the start. There's a number of processes started at the beginning as well. You can see with the darker red line, you can see the swap use starts to jump up, and memory use starts to jump up about a fifth of the way through. And you can see the memory use sort of spikes at about just after that, and then sort of dies down. So you can see there's clear behavior in there that's left behind. So if you times that by thousands, and you have thousands and thousands of malicious samples and thousands of benign samples, which is what we collected, run those in a sandbox so that you can collect this system activity as they're running. The question then becomes, how do you sort of how do you identify what's similar then and create this sort of DNA profile? So to do this, we use self-organizing feature maps, which effectively use a 2D space, or we used a 2D space with them. And they can be of different sizes. So the ones you can see on the screen here are 50 by 50 maps. You can make those whatever size you wish experimentally. So initially, if you were to just cluster everything, it would look like the diagram on the bottom right-hand side, where you've got the multiple colors all scattered all over the place. There's no sort of cohesion in that at all. But the way the self-organizing feature maps work is you take a seed point on the map, could be anywhere, you find the first data point and you map the behavior of that vector, which would be the time, the process, not the time, sorry, the processes, the process IDs, the CPUs, memory use, swap use, etc. And you map that onto the self-organizing feature map in relation to the original seed node. So obviously the first time you do it, it's going to be very close to the seed node because that's the first thing you've put on there. Over time, though, you then add another one and another one and another one. And eventually the feature vectors that are similar will stay close to each other in terms of their node position on the map. And ones that are different will move away. So over time, you essentially will get what you've got here on the bottom right-hand side, which is similar things close together and different things pushed away. So you can see with the colors example analogy here, you've got the yellows, the reds, the greens, the blues. They've all been pushed into the corners because they're similar to each other, but different to the other colors. And then you've got these sort of blurry boundaries between them where it's halfway between green and blue, it's halfway between yellow and blue, etc. And the idea was that the data would do the same. And this then helps with, for example, changing malware that's doing similar things broadly, but not quite the same. You'll get that sort of fuzzy boundary will be able to be picked up. So this was the principle, that we would organize all this malware from thousands of samples using a self-organizing map, and it would end up with what we've got in the bottom right-hand corner, which is segregated malware behaviors. So in theory, then, the principle is you have a new executable that comes in. You start to take its behavior monitored from the system every second. You feed it into the algorithm, which first determines whether it fits best with the good behavior or the bad behavior that's seen before, and then it will plot it on the good or bad map accordingly, depending again on what it's seen before, whether it's similar to behaviors in which node. It'll identify the most appropriate node. Then what you'll get is what you now see, which is basically features that represents X and Y coordinates from wherever it's landed on the node. Even looking at it now, you can see that the behavior where it's landed is in the bright red zones, which suggests very frequently seen malicious behavior. Although you've got some in the good map and some in the bad map, it would appear that just looking by eye that this would be more likely to be malicious than benign. What we do then is we've effectively transformed the data now from continuous machine activity data to a more discrete XY value. And we basically fed that into a voting algorithm, which used a sort of a combination of a logistic regression and a couple of other ML algorithms to determine how best to use these XY coordinates as features. Then it will give you a classification result. So we've gone from broad system data, XY coordinates, into a vote classifier with a number of different classifiers behind that, the most highest probability of which will give you the result of whether it's malicious or benign. So this worked very, very well. Actually, this was over 95% accurate. And when comparing to using the same approaches using, the standard off-the-shelf algorithms such as decision trees, neural nets, etc., this actually outperformed. So good bit of work. So that sort of gave us some confidence that the methods work. So it also gave us confidence in the machine activity metrics. This was one of the first times machine activity metrics had actually been used. The majority of literature in the sphere uses API calls, so calls to the system that basically are OS level calls, depending on what the software is actually doing. But we then asked the question of, okay, right, so should we compare this then, the machine metrics, which are working well, to API calls, because, well, that's the majority of the literature. Maybe that might work better. But the reason we didn't do that initially was because API calls, in theory, will create quite sparse feature matrices, right? Because they become deprecate over time. They they'll come and go as well. They'll basically be used in different ways. So as the software development has changed, they might use different API calls. And the problem then is as your malware changes over time and the API calls become less popular, you then end up with maybe 2 out of 10 features being used rather than all 10. Whereas the machine metrics, because it's continuous data, they're used by every sample, so they're always used. So that while that changes over time, the data will always be there. So in theory, it was a comparison between sparse and complete feature matrices, and we tested this by bringing in an additional unseen data set that was basically left out of the training phase. And what you can see here are 3 sets of results. They're all for executable file types. The left-hand side graph is for a random forest, the middle is for an SVM, and the right is for a neural net. The orange dots basically represent the test set that we used effectively to train the model, and sorry, other way around. The blue dots represent the data we used to train the model. The orange dots represent an organizational test set that was collected after the fact, after we'd trained. So what you've got then is blue dots. In terms of left-hand side of each chart, you've got API calls. The middle is machine metrics, and the right-hand side is combination, basically. Do they work together? And you've got that for all 3 charts. So if you start with the one on the left, for example, you've got API calls, which were up, clearly in the 90s in terms of accuracy, but drop significantly down to 70s in terms of accuracy when using this organizational test set. The machine activity metrics for that same chart on the left-hand side are fairly stable. And when you combine them, again, there's a drop in performance, but we would interpret that as probably because of the API call inclusion. So then you can look at that for SVM and neural nets as well, and you'll see in all cases the API calls drop the performance when using an organizational unseen test set, but stay reasonably stable for machine metrics in all cases. So which suggests in theory that the machine activity metrics are showing better consistency for detection over time, right? So while we've trained and tested on the day with a particular data set and even a held out test set, when we have an organizational test set which is connected later in the future after this model has been built, this is what happens. So quite an important one, because the majority of the literature still uses API calls, and machine metrics are showing better in this instance. So, all right, so we're now able to detect attacks, high accuracy. We know sort of quite a bit now about our features and how well they work. So our next question was, can we actually use this data then to predict malicious behavior? Because previously we're collecting all this data for 5 minutes at a second by second level, and we're making a decision on whether something is malicious or benign using that 5 minutes of data, which is great, but you're then saying, right, well, we've detected a piece of malware, but it's kind of too late because we've now got to go and remediate that, and there's an issue with the system. So our question then became, can we predict this actually in the early stages of a piece of malware being run, so we could actually do something about it? So we began to use neural networks, recurrent neural networks in particular, and more specifically experimented with LSTMs and GRUs. And we fed the same data in second by second level, and we trained the model. And you can see there's the processes, process IDs, CPU use, CPU system use, and we feed a file in, and the data is coming in now on the left-hand side. You can see it changing. That's the machine activity metrics being fed through the neural network. And every second now it's making a prediction as to whether it's malicious or benign, and how confident it is that it is malicious or benign. So in that way, in this instance, now you can see that's 100% benign. This one is sort of half malicious, half benign, comes to the conclusion it's benign, and it is benign. You can see this is flipping towards the malicious side. Yeah, 99.8 sure it's malicious. Yes, it is malicious, and so on. So what that was actually able to do was say, basically within 1 second, and every second then up to 5 seconds, we're making a decision as to whether it's malicious or benign, which then allows us to basically say, right, well, if we're 99.8% sure it's malicious, maybe we could do something about this. So we built this model. at 5 minutes initially, that was our sort of initial baseline model. It was 98% accurate. For 20 seconds, it was still 98% accurate, and at 5 seconds, it was still 94% accurate. So at 5 seconds, it was 94% accurate in making a prediction as to whether something is malicious or not, which is a big step forward because there wasn't anything that could do that before. We tested this then on an unseen ransomware data set, and we were actually able to find that 99% of ransomware was detected within 1 second of execution, which is like, wow, because, essentially ransomware is a huge problem, and potentially devastating to enterprise networks and lots of other sorts of types of networks, but particularly enterprise networks, because it effectively shuts down business, right? So brilliant. We can now detect ransomware using the same data within 1 second of execution. So again, begs the question, what do we do about that? So our next stage was then to think about, okay, so we can now detect ransomware and all sorts of malware actually within 5 seconds, 1 second at a very high accuracy level. What can we do about that? So we started then thinking about detecting malicious programs and then automatically killing them. So you can see here that we've got an example of process A, executable that spawns process B and C, and they run over a period of time. So in theory, if we can monitor these processes and detect that they are malicious, when process D starts, and we realize within a few seconds that it spawned process E and F, and process E and F seem to be malicious, or D seems to be malicious, whichever, we can then kill it. So we can actually say stop process D because it's malicious, which will also then stop process E and F. So essentially, that can then kill the process, protect the system. So what we did was to associate the machine activity metrics that we collected with the processes that were creating those metrics, apply our methods for detection of early stage attacks, and then kill the processes that were underlying them. So we've actually got better results than this even in the last month or so. So the initial results were the 50% fewer files were encrypted, and 90% of ransomware files were detected. That 50% is now in the 80s. So we've actually been able to improve this. The key thing for us is that the false positive rate is still around 15%. So we're killing 15% of files that we shouldn't, which obviously, if this was you and I using our computers on a daily basis, would be infuriating. This potentially could be killing this Zoom call because it thinks it's malicious. So that's probably unacceptable. So we're still working on that for real world applications, but in theory, it's a big leap forward in terms of protecting our systems. Okay, so that brings us to a point where we have, oh, hang on, sorry, I didn't expect that. Play from current slide, go back. Yeah, that brings us to a point where we've got detection, prediction at an early stage, and now automated response. And so we're sort of working on that automated response and keeping that sort of research going. We're now moving that into a sort of a more of an artificially intelligent response now. There's less data driven, more about potential expert knowledge based possible modes of response, including process killing, but also other types of response, and thinking about how we can create more of an intelligent agent-based response. So hopefully in a year or two, I'll be able to give another talk and update you on that. So another area of work that is based around the data side of life is the security of the security. So I've just shown you models that we've built that are all machine learning based models, whether it be self-organizing feature map or a recurrent neural network. The image you can see here on the left-hand side is basically the benign and malicious data presented in a two-dimensional format that clearly shows a distinction between them. This is the model is clearly able to say, although it's not one line that you could use to cut between these. Arguably, why a self-organizing feature map and a neural network is performing better than a random forest or an SVM. But you can see that there's clear lines of distinction between them, right? So that's why it's able to perform so well. So the question we asked then is, all right, so this is good, but what could we do with that to make that not work? How could we potentially move this data around so that when it's fed into the model, actually drawing these lines between the different data points is a bit more difficult to do. So this enters into the field of adversarial machine learning, which I'm sure you're all aware of. The classic example is the manipulation of the pixels on a stop road sign, where the autonomous vehicles, for example, would read that and think we have to stop. And some work out of MIT, very straightforward manipulation of the data, showed that stop sign then was not readable by an image recognition algorithm, just by manipulating some of the pixels in it, even though to you and I would look like it's still exactly like a stop sign. So this is a concerning element. So we're sort of looking at this now in the perspective of cybersecurity. So what we've been doing is basically manipulating the data. We've been doing a bit of work. We've used the IBM toolkit, the ART toolkit, and I've also been doing some work with Microsoft and their new counterfeit toolkit, which is based around that as well. If you're looking in this area, I highly recommend you look at the counterfeit tools. Good bit of kit. It's got a whole bunch of adversarial attacks in it. And so the example on the right-hand side here is with the adversarial samples included. So you can see the benign samples are pretty much where they were before, but in manipulating the data as it's fed into the algorithms from the network traffic, i.e. basically, or system level traffic, basically doing different things on the system. You can see that it still identifies some of the adversarial behavior, which is the blue dots, but also the blue crosses represent unidentified adversarial behavior, because this has now been pushed too close to the benign activity. The algorithm is no longer able to identify significant amounts of the malicious activity, which then means it goes undetected, which then means, well, two things. One, our machine learning methods for detecting and killing processes is not very good, but two, it raises questions about how well we need to ensure the security of these systems before we start deploying them. So if we start relying, for example, on an automated AML-based approach, then that this is going to be potentially a problem, because people could be subverting it. So we almost now need an antivirus for our machine learning-based detection models, right? Because we need to be able to detect that this side of activity is happening. So we're working again, this is with a project with Airbus again. We're working on this project to first of all, identify that we've got adversarial behavior, and then update the models to be able to deal with that, either through training them in what adversarial behavior might look like, so it can recognize it and flag that, or somehow building some sort of resilience and robustness into these models. So we're looking at that. That's an ongoing project right now, so keep an eye out for that one. So that's it. That's the end of my talk. So thank you very much for listening, and I'm happy to field any questions.
Right. Thank you, Pete. That was a great talk. I've got a question here from one of the participants. Might be a bit technical. So in your self-organizing map slide, I think you mentioned something about using logistic regression.
Yeah.
Is there any particular reason why you use logistic regression instead of maybe another method?
Well, so we actually experimented with a number of methods. The rationale behind using a logistic regression, because essentially it was a binary choice at this stage, malicious or benign, and we were using sort of more discrete features. So it kind of made sense to use that. It also included a number of different algorithms, and we experimented with the vote decision just to try and essentially look at what algorithms were making the sort of correct decisions, what weren't, and how was that sort of performing. And actually the majority of the time logistic regression was being used by the algorithm because it was coming out with the highest accurate probability of the correct result, essentially. So it just performed particularly well in this instance. But yeah, we did baseline against a number of others.
I see. Right. I hope that answered the questions. I think that was from Afif. Yes. Okay. Is there any other question from the participant? Yeah, Michael, please.
Okay, thank you, sir. Can you hear my voice?
Yeah.
Yeah.
Yeah, thank you. Firstly, great presentation, Pete. I really love the idea of having the AI to enhance the security. But I have the question. So you already said about the adversarial behavior in your last slide, I think, that it cannot really detect if there is some adversarial behavior, because as I see in the data, there's a lot of access, like a lot of adversarial access that cannot be identified. So I actually just want to ask, if and only if there is someone or something, or if the attacker can actually find a way to optimize the malicious executable so that it runs more likely as a non-malicious code, aka like the adversarial behavior. So will the model generated before will still works? And if not, what will the system will do to the malicious executable that been through and detected? Thank you.
Yeah, okay, thanks. Yeah, so it's a good question. So essentially, yeah, if you were able to do that, and one thing you might do, for example, is to pad the sample with some additional CPU traffic or whatever to try and make that incorrect decision. And then ultimately, if you're able to do that, it will pass through the detection system and it will execute on the system and it will cause you problems. And so this is one of the things that we need to do. And so our plan is ultimately to expect that, to anticipate that people would do that, and almost to add a third class into the detection problem. So you've no longer got malicious or benign, you've actually got malicious, benign, and potentially adversarial. So it looks like this could be malicious because actually it doesn't really look like benign or malicious. So this is something that's quite unusual. A heavy chunk of CPU injected over a prolonged period, for example, might make you think, well, what's this? What's going on here? That's quite unusual. And then flag it as adversarial. So if we can do that, and we'll do another set of experiments to see if we can determine malicious, benign, and potentially adversarial, we can then start developing confidence levels in the adversarial detection. And then again, the same with the process killing, we can have a threshold defined for the adversarial, potentially adversarial, where we say, yeah, this is potentially adversarial, so we'll kill it anyway. So that's what we're sort of experimenting with at the moment, which obviously leads to the question of, okay, well, then I could actually potentially perform a denial of service attack by making everything look potentially adversarial, and then it kills all your processes anyway. So that's an interesting bit of work that we'll do after that again. So yeah, I mean, it's a really interesting place for us to be at the moment, because we're effectively trying to break the security mechanisms that we've now built. But I think ultimately that's the way we need to be, because again, as I said, if we can't get confidence that these methods can work and work in a robust way, they're not going to ever be used. So there's a whole bunch of work we need to do around that. Hopefully that answers the question.
So for the current system, there's nothing we can do about the undetected stuff.
That's right. Yeah, if it's undetected, it's undetected. I mean, basically, like going right back to the start where I was talking about why we started doing this in the first place, because you've got antivirus that people can work around. It's the same principle. If there's a workaround, there's nothing we can do about it. But that's led us to this next piece of work now, where we're actually looking to build in mechanisms to deal with people working around the machine learning.
I see. Thank you for your answer. Thank you, sir.
Right. We've got another question at the chat box. How can we visualize training process of the machine for deep learning? I think you showed the visualization of your RNN model. Yeah.
Yeah. So how can we visualize the training? So what we have done before is to visualize the weighting associated with the nodes in the neural network. It gets quite complex, though, because as the network grows, it becomes quite hard to sort of interpret. But where I showed you that image before, I mean, that was essentially a JavaScript image where you can have data behind it and hover your mouse over it and it'll show you what's going on. So in theory, we did a piece of work. I think we published it in Asonam in 2015, where we actually pulled apart the nodes and the weightings in the nodes to try and understand what decisions were being made through these nodes. And we were actually able to examine the nodes and say, well, this node is actually based around things where you've got a high CPU rate and a high number of running processes, and this node was actually related to the high number of bytes into the network and a low number of bytes going out of the network. And we were able to then associate those also with whether that was a decision towards being malicious and a decision towards being benign, which then it's difficult, but then somehow allows you to sort of unpick what's going on. And you're able to actually say, right, well, the malicious stuff is being classified because, and give you the idea of what's going on in each of those nodes. So that's one way that you could do it. But as I say, it gets complex if you start building large, deep neural networks. It becomes more and more complex to do it. And obviously, the more features you feed into it as well, the more problematic it's going to be to interpret that. I mean, we've only got 9 features in this model. If you were to include thousands of features, which you would if you did, for example, API calls, it becomes very hard to interpret. But that's how we've done it.
Right. I think that answers the questions. Any other question from the participant? Well, I've got a question too, Pete.
Yeah.
So you mentioned something about implementing this, your approach in a real life stock. What do you think are the challenges to implement this or your approach in a real life stock?
So the main thing we're seeing at the moment now is basically SOCs are run by people. People need to make decisions on whether something is legit or not. Essentially they need to say, oh, I've got this alert and I need to dig into it and work out whether this is a real attack, whether it's a valid alert, and what to do with it. So we've shown sort of the outputs of some of this to them, and their first question was, how do you know it's malicious? And so that's where we started to work towards the visualization of the neural network. But still, it does beg the question of, how do you know it's malicious? How can you be sure that this is something malicious? And that's hard. So actually, one of the things that we're doing in this current project, where I was talking about the adversarial stuff, is also to look at the explainability side to try and actually give a decision. So not just a confidence, but it's a confidence of 99% is malicious because, and then trying to extract the decision process of the model to try and sort of, it won't be plain English, but give some sort of near to English representation of why it's made that decision based on the features it's used. So that's the first thing is that. The second thing is the resilience side. So if we deployed this today and people believed that it was a valid model, would they still believe it tomorrow or next week or 6 months time or a year? When's that cutoff point where you start to think this model is no longer valid? Because as we showed earlier in the research around the different data sets, as software changes, the features will change, machine activity will change. And is the algorithm still making the correct decision when those features change? So there's a question of, how do we know when the features that we're using to make this decision have changed so much that the model may be no longer valid? And that's a PhD project we've got running at the moment, because that's another question that people will ask in the SOC. So ultimately, it comes down to the resilience and robustness and the explainability of these models in an environment that is led and driven and operated effectively by people. And it comes down to the trust, the confidence, and the belief, I suppose, that the system that we're putting in place is going to do what it's supposed to do over time. And that's going to be our biggest challenge, because unless we can answer those questions, including the things like adversarial attacks and how people could work around the system, it won't get accepted in SOC or by SOC operators, and it won't get deployed. So it's a big challenge for us now. Over the next, say, 3 years, we've got this project running to try and convince, I suppose, SOC operators that this is a valid and robust and trustworthy model, which is not easy. So they're not really technical challenges, other than trying to explain technical things to, well, technical people, but people who don't understand machine learning in the most part. It's actually very much a social concern and a human-based concern. That's going to be our biggest challenge.
I see. Thank you. Yeah, so we've got other questions from the chat box. Since AI-based methods usually require data in order to build a well-trained model and resources to perform computation, how do we deal with security issues in mobile devices with limited resources?
Yeah, good question. We were literally just at a PhD start around that as well, sponsored by Toshiba. So one of the things we've looked at previously is what we call sometimes called transfer learning or model distillation. So you can actually create a lighter weight model from a more heavyweight model. So for example, you can train a decision tree model from a deep neural network. So the deep neural network will obviously, potentially need a bit more computationally intensive resource. So particularly if there's lots of data going into it and it's quite a big model, lots of features, etc. As that grows, it'll need more resource and potentially won't work on a lightweight edge device. So model distillation is one way of doing that. And the question then is, how accurate is that? How much of the performance of a deep neural network can be retained when training a more lightweight model? And how is that retained over time on different data sets? So that's another problem we're actually looking at the moment. But that's the principle, is to try and transfer the knowledge or the learned model of a more complex model into a less complex model without losing performance.
I see. So essentially, one of the solutions is to transfer the learning from the more complex model to the simpler model.
Yeah. While obviously trying to retain performance, because the complexity in a deep neural network just can't be sort of pulled into a decision tree. You can't have that level of complexity is too much. Or if you did have more complex, more decisions, then you'd be making lots of decisions and potentially becomes more computationally intensive anyway. So that's the question. But that is the approach that we're taking at the moment to looking at that.
I see. Does that answer the question, Swardiantara? Okay, thank you. Is there another question from the participant? Okay, if not, I've got another question for you, Pete. So I was wondering if there's any specific behavior for its type of malware. For example, whether the ransomware may have like huge CPU usage or lots of open files, while maybe the other type of malware has something different.
Yeah, that's a good question as well. My instinct is yes, it does. And that we could probably, for example, create separate feature maps for different types of malware. What we've done is we've actually created a single one, and we haven't split it apart and trained separate ones. But I think potentially we could, and I think potentially it would improve performance. Ransomware is an obvious example, as you say. In theory, it would ramp up the CPU because of the file encryption activity. Even actually, if you included API calls in that as well, you'd probably have a very solid model, because it would be calling files all the time. And if you're doing that over a time-based model, then it would, in theory, it would pick that up quite quickly. Other types of malware, I don't know, and we haven't done it, but it's certainly worthy of a project to look at that kind of thing. Actually, if anyone was thinking of doing another project, a comparison of different types of malware using a single model versus multiple models in this particular case, to determine and to look at the previous question, some of the explainability element, to explain why these models were working in that way and what sort of activity they were using to make decisions on, for example, ransomware versus Trojans and spyware and so on.
Right. Thanks. Yeah. So that leads to more questions in the future, and maybe there's something that all of us can collaborate with. Okay. Is there any more question? Maybe one more question from the participant before I wrap up this meeting. Okay, I think we don't have any more questions. Okay, first of all, thank you, Pete, for coming, not physically coming, but it's
no problem. You're welcome.
Yeah.
Thanks for the invite.
And yeah, so just to wrap up, I think I can just summarize few points from the presentations. So here, Pete is doing cybersecurity analytics, where he combined various what's called department or school at Cardiff University, from computer science and criminology, psychology, law and politics. And then in his research, he has done several research about risk assessment and then risk communication, and then mainly AI for data-driven analytics. And one of the case study that he presented us is about the SOC at Airbus, where we can learn how to distinguish malicious and benign software. So we started from the feature map of the malicious activities, and then we moved on to the comparison between machine activities and API calls that actually shows that machine activities provide better consistency at distinguishing malware and benign software. And we also see how the early malware prediction can predict malicious activity in the first 5 seconds with the accuracy of about 94%. And then in the next research, he also presented about how the model can kill malicious process. So instead of just detecting the malicious process, it kills the malicious process, and it helps in reducing the effect of ransomware. So we've got lots of questions. We've got new things that we can explore. So thanks, Pete, for that. And on behalf of the informatics department, I would like to say again, thanks for talk, and hopefully we can do more collaboration in the future.
Definitely, and thanks very much. And just to add as well, the work I'm presenting is not just my work at all. There's loads of people have contributed to this, and in particular, Matilda Rode, who is a PhD candidate who's just finishing up and has now gone on to work at Airbus, has contributed an awful lot of materials to this, as is Matt Hopkins on the last slide. So just to add that as well, this is the outcomes of a very much a team-based approach. So, to bear in mind as well is that there's a wider team here. Check out our webpage. There's lots of activity going on. If this isn't directly related to your area, I imagine there might be someone in the team who is, and do get in touch if you'd like to collaborate on anything.
Sure. Thanks, Pete. Thanks everyone for coming to the talk. I guess that's all for this session, and I'll see you again in the next opportunity. Right?
Thanks, everyone. Bye-bye.
Bye-bye. Gonna end the meeting.